All right. Hello, everybody. My name is Thomas Versich. I'm a master's student at Texas A&M University, and today we'll go over developing a Modelica model for the Texas A&M Smart Connected Homes testbed. So you can see in the bottom picture here, these are two identical residential buildings that we have on the Texas A&M campus. They are essentially mobile homes. If you've seen them on trucks on the road when you go down the highway, they were built in Waco, Texas. And then constructed around this time last year over on the A&M campus and connected together. So these two buildings are used for grid interactive efficient building technology testing, as well as smart home technology testing. They're both identical, like I said, 1,200 square feet, typical single family house, 3-bed, 2-bath. And they also do come with a configurable floor plan. So some of the walls inside are removable. The houses they come standard all electric, so all of the equipment inside of it. They also come with overhead and underflow duct, LED lighting throughout, and then the air conditioning unit, there's a 2.5 ton 15 SEER, and then it has an indoor electric furnace, which is 3 ton. And so most of the work done for these homes for modeling has been using the Modelica Buildings Library package in Modelica, so that we can build the homes actually in simulation and use these as part of our research before we move on into the experimental phase of this work, so that we can have a model to compare to once we're doing that. So the process that we wanted to go through was to split the homes into 3 separate zone models. So a crawl space that's underneath in which the foundation is built on, the actual floor space of the zone where the occupants would live inside, and then the attic space. Actually, the attic you can't really access as an occupant, it's closed off. And then the model of the HVAC, which is just a split system air conditioner unit. So when we move into the thermal zone modeling, what we do is we are using the Modelica Buildings Library mixed air model, and we use 1 zone currently to model the entire building. Excuse me. And then the windows on the north side is going to be 4 square feet. On the east side, 60 square feet of window area, 15 square feet in the south, and 31 square feet on the west side. And the thermal zone is about 8.5 feet high. And these boundaries of this thermal zone are shared with the attic and the crawl space, as we know. And in Modelica, what we do is we define the constructions of the thermal zone to be construction boundaries inside of the thermal zone. And when we define that same layer in the crawl space and attic that are shared, so the floor and the ceiling, those are treated as surface boundaries so that they are shared the boundary conditions when running a model. So the hardest part probably over the last year has been trying to get the exact material properties that were used by the building manufacturer. So as you can see in the top part, those are the words from the senior engineer at their headquarters. So we had descriptions of what building materials were used, but not the exact materials. And so over the past few months, we've been trying to get the exact materials used so that we can model these and to have a detailed building envelope model, which has been a little bit of a headache. So we know what I was able to do was find the actual materials inside the homes. So like the gypsum board, I traced back the manufacturer to find exactly what it was made out of to do that. Also, as you can see here, there's a part that says R13. It's in red because that is kind of a discrepancy with the actual on-site installation. So when these homes were constructed and installed on the A&M campus, we actually have a sheet that has an inspection of all the installation that was done in the floors, the walls, and the ceiling. And so the walls actually are R19. So the information from the building manufacturer couldn't rely heavily on. So I think what we did was mainly try to find the source from the material and actually find the real material properties from there using our sources online. Some other sources that we were able to find online were the linoleum flooring, which is not a wood, it's like a covering, the architectural shingles on the roof, and the OSB decking So some of these sources came from the IECC code standard that building manufacturers use for their materials in the same climate zone. So some of this information could not be found specific to the house. So we had to use the information that was available online in the code compliant house information. So I'll go through kind of the floor space model. This is where the occupants live. As you can see in the top left, there are all the detailed model properties and constructions defined, kind of like just what I went over. These also, the mixed air model gets internal gains from the zone due to occupants, and right now they're a little arbitrary. We have done methods to calculate the internal gains using NREL, some procedures from NREL that were developed for simulating occupants inside of a building without actually having them there. So we do have occupant schedules for weekends and weekdays, and we hope to implement this in the zone later. The floor space model also has air supply and return ports for the HVAC connection on that left side. And then the boundary conditions defined for the attic and crawl space zones. So on the top and bottom are where we have the connectors that will be connected to the attic and crawl space models. Kind of like how we discussed before with the construction layers and the surface boundary layers definitions. Here we'll move on to the crawl space model. So the crawl space model is just constructed out of plywood skirting. That is it. There's no holes in it. There's nothing like that. There's no internal gains being produced inside there. So following the engineering floor plan, we're able to construct the same way we were doing the floor space model. We're able to construct this one with just a very simple plywood skirting around it. Also, you can see on the top, we have that heat port that we connect into the thermal zone, and this is defined as the surface boundary. And we use the average ground temperature for Bryan, Texas, where these are located for the heat transfer through the ground. Actually, we had a hard time finding the material properties. There's actually a white calish rock foundation that is laid. So for right now, we just assume a small layer of, of concrete that is built upon. And then I'll move to the next model. So here we can see the attic model that is made. Same thing as the other ones before. We use the engineering drawing to construct this inside of Modelica. There's no internal gains in here because there actually is nothing inside of there in the attic. There's no way for any occupants to access it as well. The bottom heat port is the same surface boundary connection that goes to the ceiling of the thermal zone where the occupants are at. And excuse me, the roof is oriented in a double pitched manner. I don't know if you saw the picture before. It kind of just looks like this picture on the right here. So the way that we have to define that, actually, I'll move on to the next slide for the demo. But when we talk about the surface definitions and walls inside of the Modelica Buildings Library, when we're constructing the envelope, there are certain constant definitions that we use for walls, floors, and ceilings, as you can see there. So following the building definitions of walls, floors, and ceilings with regards to the occupant, for an 11-degree double pitched roof, which is what the engineering drawing says, we actually define it like so, as you can see in the bottom. So just 11 times that pi over 180 to get the 11-degree angle, and then we use the azimuth definition to tell the buildings library what side of the building it's on, east or west. Then we move on into the air conditioning HVAC model. So for the purpose of this paper, we have only looked at the cooling HVAC loads for this. It does have electric heating, but we have not gotten into that yet. So for the air conditioner HVAC model, we use a single-speed DX cooling coil, and the indoor blower inside of the lab homes is actually a single speed as well. And to operate this, currently we only use a simple rule-based control inside of Modelica right now. So we have our 75-degree Fahrenheit temperature set point, and then we have a 2-degree Fahrenheit dead band. And so the cooling turns on when the temperature is above that dead band, and the cooling turns off when it is below that dead band. And so for the DX cooling coil model, what we need to do is have the cooling capacity and energy input ratio performance curves for the actual split system that we have on site. And so to do this, we actually need to find the AHRI rated performance data, the catalog data for this equipment. And so moving on here, the cooling capacity function in Modelica, you'll need to specify the cooling capacity is calculated using some modifier functions. So the first modifier function is due to the change in temperature from the evaporator inlet and the condenser inlet. You also multiply that by the modifier function for the changes in flow, and then you multiply by the nominal cooling capacity. And actually, the same goes for the energy input ratio, which is just the reciprocal of the COP. So you have the modifier functions based on the temperature inputs at evaporator and condenser inlets, and then the flow, and then you divide it by the COP nominal. This is how the cooling capacity and power usage is calculated for the DX coil. And actually, for our case, we actually simplified the modifier functions for flow based, we set this equal to 1 because we have a single speed in coil, so we didn't want to worry about so we didn't include that inside of our modifier functions for the cooling capacity and energy efficiency input ratio. So moving ahead, on the bottom left, we find the AHRI rated conditions online as best as we could. The wet bulb temperature on that left side is going to be the evaporator inlet temperature for the coil, and on the right side, we see, on the headers to the right of that are the different outdoor conditions that are seen by the condenser inlet. So using this data, I used Python scikit-learn to do a linear regression model to find these coefficients that we could find for the input of the performance curves and the DX coil, and then the results are just on the bottom right here. So initially, what we wanted to do, because we actually had no data collection on site until this summer, we did what we called intuition checks, so that we would run these thermal zone models just with some local TMY3 data and kind of just spot check it. So this is not really a validation of our models, but this is just an intuition check. So we had like our crawl space and our attic models were just run using the ambient conditions with weather, just so we could see how the weather affects it and if our building envelope models made sense. Actually, for the thermal zone model, we connected just an arbitrary fan blowing outdoor air inside of the model. So these are just validations to show kind of the results on the bottom. On the right side, we can see that that's the plot for the attic temperature, and it follows directly the global horizontal irradiance that we see locally. So that we think that those made pretty good sense. So we wanted to make sure we move on and do a spot check for the cooling coil, for the DX coil that we were running. So what we did here was that we took this from an example inside of the buildings library DX coil, where they test the single speed DX coil. And what we did was we used our rating conditions from the AHRI table to test these conditions to see that our performance made sense. And unfortunately, actually, we were not able to figure out why at low wet bulb temperatures at the evaporator, the cooling capacity was not able to represent the actual cooling capacity. So that is something that we have to check for low wet bulb temperatures at the evaporator. Going back to the performance curves, we didn't see that this was an issue with our performance curves as we manually calculated the cooling from that. So we know that it must be in our Modelica model. So after all these spot checks, we decided to combine them all into one. You can see on the right side, kind of the roof-looking ones double pitched, the thermal zone, which is in blue, and the crawl space, which is in brown. So we connect these all using the heat ports, basically, which is why we defined the boundaries as surface boundaries for the crawl space and attic, and also the construction boundaries for the thermal zone. So once you connect them, it doesn't need to calculate this heat transfer twice. It actually just shares it. And then you can see our HVAC model on the left side of that, which we just connect those fluid ports for air into the thermal zone, which is how we connect it to represent the lap pumps, and just our HVAC control just right above that, the simple rule-based thermostat control that we set. So then on the top left, we see the weather input that we are using for Modelica, and in this we could either choose to use some TMY3 data, or if we actually plan to have a weather station on site to collect the local weather data so that we can run tests and compare power consumption, actual versus simulation, to kind of validate our model. And this is actually our plan. This is our plan currently. So in the method of creating a weather file, we actually download the TMY3 weather file from the Easterwood Airport, which is the College Station Airport where Texas A&M is located at. This we find on the Energy Plus weather website. We can go into a text editor and actually modify the variables inside of it. So at the bottom, you see there's 30 columns inside with relevant weather data that the Modelica library uses. So we actually go in and replace all of our weather data that's collected with our on-site weather station. And then at this time, we did not have our outdoor pyranometer set up, which collects the solar radiant data on-site as well, which will help to validate our model when we're looking at the weather conditions at specific times that we're metering the power consumption. So for this example, we used our on-site weather station that was set up this summer. Unfortunately, we didn't have our outdoor pyranometer set up, so we were able to find recorded solar data online and replace this data in the meantime. And so once we constructed our weather file to be input into Modelica to resemble the local weather at these lab homes, we did a comparison on the simulation versus the actual data that were measured. So we're actually doing circuit breaker metering so we can see the power consumption at every end use inside the house as well. For the time frame of August 4th to 11th, which is the period of time that we have collected data for the power consumption, and like I said, we used the online resource Solcast to get our solar data. So with these in our weather file, we were able to compare the actual versus our simulated power consumption of the AC unit to compare the performance of this model inside Modelica. That can be seen on the right side. So we can see that the shape of the performance of the DX coil, it actually matches up pretty well. And what we see is about a 250 watt offset. And we think that once we're able to go in and actually tune our model and fix the things that we know that are wrong, which could use more time fixing, like the building envelope detail, materials, also other stuff, like the performance curves of the DX coil. There are a few tweaks here and there that we can do and tune our model to actually close this offset and kind of match our to match our simulated data versus our actual consumption data. And just on the left side is just a validation of kind of the temperature control, that we were able to meet our temperature set point inside the house during this occupied period. And then the red line actually in that is the local dry bulb temperature that's measured from the weather station. So we can kind of see at some points there's a very steep spike, just for instances, like in the middle. Sorry, excuse me. In the middle right here, we can see a steep drop in the dry bulb temperature reading, maybe here too, and also here as well. So just standing at that, we kind of think that our weather station metering is not very accurate at some points. So maybe some cleaning up of the data would be good as well before this. So I wanted to kind of wrap up and kind of go over some of our future work, because this has been quite a learning experience, modeling a building that's already built, especially when you can't find all the information on the detailed materials or how exactly everything should be inside of the simulation. So I talked about having an occupant schedule based internal gains. So we've already created these schedules for a typical single family household. So we wanted to input this into our internal gains into the thermal zone to kind of represent what we would see there from a typical use family. There needs to be some modifications in our model on the thermostat operation. Actually, during this operation period, we had some issues with our thermostat, and we couldn't control the setback temperatures as the same as the set point that we designed it at. And then also like I discussed before, the AC performance at the low wet bulb temperatures, a little bit concerning. So I need to revisit the modifier functions and how they were implemented in the Modelica model that I showed. And then once we get to that point, we want to start to tune our Modelica model so that we can actually use this model in simulation and actually use this before we go and implement our research into the experimental test bed, so that we can kind of bridge that gap and verify this. So I think I'll end it there. So thank you very much for your attention, and I'll listen to any questions. Okay, yeah, that's a great question. So the question was, are these homes actually occupied when we're doing all these tests? So currently, there's nobody living in them. We don't actually plan to have people living in them. This is a test bed on our campus. So I think I briefly went over the in-rel procedure, the house simulation protocols. How do we simulate occupants inside the building? How do we generate those internal loads? So we started to build up these schedules to simulate what a family would generate inside this house. So we're going to use heaters and humidifiers that follow this 15-minute schedule, basically, to generate these loads and simulate occupants. And then I think towards the future, when we move into the actual research, we'll do that step and then actually have people inside kind of simulating, actually generating those real loads instead. But currently, no real occupants living inside. Thank you. Okay, yeah, that's a great question. So the question for those online, is just what was the purpose of all these modeling? Are you doing model-based control, or basically what was the point? So the big idea for this was that we wanted to do a lot of research. A lot of the research in the lab is based on simulation work, and we wanted to have to use this test bed as a place that we can start to put the simulated work into a real experimental test bed. And so building up this model for these houses will allow us to use these models instead of like the DOE prototype models, the office buildings and that stuff, and use our actual residential homes. And then so we can test it with that and then apply it into the test bed and kind of compare, okay, how does the simulated results compare with the actual results that we see in a real home? So that's kind of our goal right there. Yeah. Yeah. Okay.
You spoke about the flame oil and validated installation of the
Yeah. Yeah.
It kind of seemed like the project.
Yeah.
Did you like go back and kind of something which is validation?
Okay, so the question was, I showed a slide showing that we had low performance at the low, or bad performance at the low wet bulb temperatures at the evaporator. And so when we applied this to the real model, why did it perform like we expected? So these AHRI rating conditions, we performed poorly at the low wet bulb temperatures in the evaporator. And so whenever we run this test was actually done using data from the summertime. So we saw high temperatures and we actually it didn't have to go down to that level. But it's still like, because we want to use this model, we still want to go back and validate and kind of figure out why we're having low performance there. But thank you for your question. Yeah. Thank you guys.
All right, so next up we have Hongtao Chow from the Mitsubishi Electric Research Laboratories, and he's going to talk about the performance enhancements for zero flow simulation of vapor compression cycles.
Good morning, everyone. My name is Modelica. I'm a research scientist from Spatial Research Lab, and this is the work that I work with my colleague. So the motivation of this work is very obvious because we are doing a lot of numerical transformations for computer systems, and we often encounter relevant applications. For instance, if we want to stop the system or shut down the system, and also if we want to switch the operating mode of the system, and even we want to do the reverse cycle processing, and especially for the very refrigerated flow systems with a lot of units. Sometimes you want to turn off one or multiple window units. So in these conditions, we often encounter zero flow conditions. So there are not many people addressing zero flow transformations. Particularly, there's one paper in 2016, and that paper addresses some approaches and proposed some guidelines in terms of how to improve the speed for zero flow transformations. And we went through that paper, and actually we implemented all the approaches, but we still found that those approaches are not very satisfying in terms of the speed. So we say, okay, maybe we want to do a bit more research and explore some numerical techniques in terms of further speeding up the simulations. So this is how this work comes from. So in terms of vector control system, so here we have a very basic cycle here. We have a compressor, condenser valve, and then evaporator. So typically, the vector control system, the most important component is the heat because they are used to exchange mass, momentum, and energy with other secondary fluids. And in our work, the heat chain models are based on the convection laws, and for the compressor and the valve, they are modeled using the components map, which typically can be obtained from the manufacturer. So I think the most crucial aspect of modeling the heat exchanger is how to describe these ingredients. So I think the most commonly used approach to describe those common ingredients is to use pattern one method, and this so for pattern one method we have to use static weight scheme because it has been proved to maintain the physical quantity. So here we will have two types of cells. Flow cell and volume cell. So basically, you will calculate the momentum balance through the flow cell, and you calculate the energy and the mass balances in the volume cell. So that you can discretize those condition laws. But the thing is, there's not much you can do about the mass balance and the energy balance because it's a very standardized form. But in terms of momentum balance, we can do a lot of model function in terms of improving the speed. For instance, here, if you look at this term, this is actually the initial term, and this is the dynamic pressure term. And also, we have this gravity effect here. So the problem is, for the vapor compression system, we are not dealing with, for instance, the sound wave or pressure propagation, because in that case, these two terms will be very important in terms of predicting the pressure propagation. But for our purpose, we often neglect the inertial term and the net pressure term here. So we have evaluated several model reduction techniques in terms of how to deal with the momentum balance. For instance, okay, we assume that the derivative of pressure is spatially invariant along the length, and also we can assume that the pressure is linearly distributed along the length. But we found these two reduction techniques are not very helpful in terms of, first of all, maintaining the mass conservation and also improve the simulation speed. So finally, we said, okay, we can do further reduction. We just consider the frictional pressure loss, then talk about all the other terms. And then we found this, actually, this form actually has the best performance in terms of speed and also would generate reasonable accuracy for the simulation results. But also, there's still one thing for this form is that how can we calculate the shear stress, which comes from the pressure correlation. So, okay, we say, okay, we can further simplify the pressure calculation. We just assume that the pressure loss is a function of the mass flow rate, and then we can we will ignore other effects, for instance, the quality, density. Then we can do the curve fitting for these two constants and the number, because these two constants will be generated based on the theta pressure correlations. But the problem is here, if we invert this form to have a function of a mass flow rate based on the pressure, if we calculate the derivative of mass flow rate with respect to the pressure, we can see that here in the denominator we have this mass flow rate here. So it means that, okay, if the mass flow rate goes to 0, and that this derivative will go to infinity, that was the summation stuff when you have very low or zero flow conditions. So we say, okay, we need to do something about this. So the remedies to regularize the relation with non-singular substitute around the origin of this relation. So actually in Modelica there is a built-in power function to do the regularization for the case that I talked about. But the problem is they just use this linear, so which B is 1 here. So basically what that function does is, okay, we just linearize the relation around the origin. But we use that built-in function, and then we simulate our cycle models under zero flow condition. But we found that the speed is still very, very slow. And then we say, okay, maybe if we somehow we can reduce the slope of this approximation around the origin, maybe we can improve the speed. So that's why we say, okay, instead of using this linear approximation, we can increase this power constant and have a cubic approximation, so that, okay, the mass flow rate will be much less sensitive to the pressure. So that, okay, have, let's say, if we have some modest pressure change, but the mass flow rate will not be that sensitive, so that you don't get the high frequency oscillations for the mass flow rate. So the whole purpose is to reduce the Lipschitz constant of this approximation around this region. It turns out this very simple change will make a very, very big difference. So I can show you a study here. So this is a heat pump cycle model. So we built all these models in our lab. And the size is it's not very small. So you can see that the entire cycle model has more than 1,400 equations. And if we use, actually, yeah, the system will be shut down at 500 seconds, and then you will remain off for the rest of 4,500 seconds. So the thing is, okay, if we just use the built-in regularization, which approximates the pressure relation using linear profile, we can see that, okay, this is very, very slow. It will take more than 7 hours to finish 5,000 simulation. But if we just use cubic approximation, you can see that the speed can be improved by 10 times. Just, I mean, everything else is the same, you just change that parameter. Don't do anything else, just change the speed from 1 to 3. Actually, we explored some other approximations. So we found as long as we found when B is bigger than 3, I mean, the improvement is just it's pretty much the same as B equal to 3. So we said, okay, maybe we can stay with the 3. So another thing is that, okay, how to calculate the heat transfer coefficient, because for the rate coefficient system simulation, you have to calculate the heat transfer between the refrigerant and the wall and everything else. So the thing is, typically the heat transfer coefficient is very complicated because it depends on the regime and it depends on the flow conditions. So the number one rule is that, okay, you have to smooth all the heat transfer coefficients for different regimes, for instance, vapor, two-phase and liquid regime. But even that, we say, okay, the calculation still is too complicated. Okay, so we can further simplify the calculation for heat transfer coefficient. So again, we use this very simple way to calculate the heat transfer coefficient. And then we can work with these two constants. But the problem is, sometimes if you use this static or accurate relation, you will get spurious numerical oscillations when the refrigerant vapor condenses to bring the condensation. So we say, okay, maybe we can use a low-pass filter to decouple the calculation of heat transfer from other state variables. So actually, this form really helps to eliminate the spurious numerical oscillations. But we found this filtered form would increase the number of dynamic states. Actually, it would slow down the zero flow simulations. So actually, this is what we found using the previous case. If we compare these two different relations. So actually, this is different from the previous paper that was published in 2016. But anyway, I'm not saying that okay, we have to use or we should use standard form of this calculation. I think it's a case by case. If you found okay, the numerical oscillations for the heat transfer coefficient will slow down your non-oscillation, maybe you can switch back to the filter form. So another way to simplify the model structure is that okay, for the conservation laws, we have different ways to discretize those equations. So Vanderbilt method is just one of those methods. In our lab, we have models with different complexities. So we have movement method, and but this method would present a lot of challenges in terms of model structures, which because sometimes you have no vapor phase, for instance, for the evaporative phase. Sometimes you will have liquid phase for the condenser phase. So it would present a lot of challenges, but we do have switching schemes to switch in different model structures. But there's a fatal disadvantage for this form is that it cannot handle zero flow because this method is based on the assumption that the refrigerant flow flows at the inlet and leaves at the outlet. And also we have this non-parameter method, which we did last year, actually 2 years ago. This method is different from conventional non-parameter method because we have imposed some assumption in terms of how the refrigerant entropy will be distributed along the length, so that we can more accurately characterize the dynamics of the flow. But the thing is, if we stick with the Vanderbilt method, we can see that okay, the mass flow rates between these control points will depend on the pressure loss, right? And if we somehow can reduce the dependence of the mass flow rate on these pressure loss, we can somehow decrease the number of states. For instance, we can just use a single pressure for some certain control points, so that okay, you only need one pressure state to for the entire heat exchanger or pipe. But the thing is, you can still account for the pressure at the inlet or the outlet of the heat exchanger, depending on the model structure. Because sometimes, let's say, because the whole idea of staggered bridge scheme is that okay, you have to connect the volume model with the flow model in alternative sequence. So based on this model structure, actually we can automate the place where the pressure will be calculated. So in this way, we can further reduce the model complexity. So we can see here, if we use distributed pressure model, which was described previously, we can versus non-pressure drop model, we can see that the distribute time can be further decreased by approximately 9 times. But the thing is, with all the enhancements that I described previously, we can get more than 100 times speed up. So we have another case study here. So we have 2 evaporator branches, and we also did a switch study. So the system operated normally for the first 500 seconds with the 2 branches active, and the first branch will be turned off at 500 seconds. and the valve will be fully closed, and the fan, which I didn't show here, the fan will be turned off as well. And at 3,000 seconds, the entire cycle will be turned off. So as you can see, with all these enhancements, we can simulate the scenario with reasonably fast speed.
I think I can wrap up.
Yeah, so I think this is my last slide. So as you can see here, so reducing the sensitivity from mass flow rate to the pressure difference is a very important key to accelerating the simulation. And also, static or filtered heat transfer calculation is really case-by-case scenario. But also, we found if you run all the pressure drops at some certain location to further speed the simulation. So finally, we would like to evaluate these enhancements with models that can generate the analytic. Because there's a paper back to 2020, which talks about how the analytic experience can improve the zero pro simulations. So we would like to do the further study in that area. So I think this is all I have. Thank you.
That means now if the tool develops the equation, even numerically, you can have infinite derivative approach.
That's true.
And that can cause the Newton stars.
That's true.
How does that happen? That can tell me.
Yeah, that's true. But the thing is, we apply this. Yes, the derivative is zero at the origin. Yes. But the problem is we apply this approximation here instead of here. You know what I'm saying? It's because the thing is, if you look at this, if you look at the company equations here, so the pressure and the entropy will be the same variables, right? We need to calculate the mass flow rate based on the pressure loss, not the other way around. So the thing is, yes, you are right. If we apply the cubic approximation for this, yes, you cannot get a inverse function at the origin, yes. But the thing is, we apply the approximation directly here because we don't need any inverse function in this relation.
So it's the reasoning because you have mass as the state, you can guarantee that the tool does not invert that equation.
That's true.
That's right. It's not necessarily negative.
Yeah.
Okay.
Yeah.
It's not applicable in general to steady state fluid flow simulation.
I'm sorry.
It's not applicable to other fluid flow simulation like in airflow network or a water flow network. You cannot make that assertion that the tool does not invert the equation. It's very specific then for your dynamic propagation side.
I think so because I think it's more fair to say this. It's especially applicable for the models that we have. As long as you don't need the inverse function,
Yeah.
I think that would work okay. But if you want to invert the calculation, yes, the cubic approximation will, yeah, we'll have a program at the origin, yes. But we can switch back to linear solution whenever you want, because that is the parameter and can change the value.
Yeah, it's just hard to know whether someone inverted it. Yeah. Not models.
Yeah, unless you already simulate this.
Very nice talk. I was wondering if when the compressor shutdown period, do you really have the compressor speed to zero or divide that? Can Modelica solve the zero maximum static state?
I think so, because we stream connector and then, I mean, previously we did not do that, but I made some changes to the converse model, so that now we can do exactly so. Now, very small, so we can do that. But the thing is, you have to guarantee that the power goes to zero, because I think that yesterday, we had a problem. So the power has to go to zero when this, when the converse speed is zero. Otherwise, we will have using the zero error for the entropy average.
And also, like, during the shutdown transients, I found that the time constant of compressor speed and fan speed should be carefully selected, otherwise the solution will fail. I think that because the imbalance of heat transfer, at refrigerant and air side, that will blow up the refrigerant dynamics. Do you have a comment on that? Like, how fast should the fan speed also go to zero?
I think in this case, it's pretty fast. It's pretty fast. I can't remember 1 second or yes, 1 second. You can either increase if you think okay, it's a bit more challenging for the software. Yeah, you can make it 3 or 5, and really, it doesn't matter that much because the thing is once the speed reduces, the pressure goes down like really fast. I mean, I'm not sure how many people will really care about 5 second transients because sometimes accuracy have to be sacrificed for the
Yeah, I think that's
for the rustiness.
question. So
Yeah.
thanks for getting that.
Thank you. Close this. Okay.
Next up, we have Karen Faulkner from the University of Colorado Boulder, and he's going to talk about the trade-offs between indoor air quality and sustainability for indoor virus mitigation strategies in office buildings.
Oh, you can. Sure, it's fine. Yeah, that works. Yeah. Great.
All right, thank you, everyone. As mentioned, my name is Kerry Faulkner. I'm a PhD student at the University of Colorado Boulder, working with Professor Wang Zuo. And today I will be talking about the trade-offs between indoor air quality and sustainability for indoor virus mitigation strategies for office buildings. So first, we know that buildings account for a significant amount of energy consumption worldwide, particularly about 40% of total energy consumption in the U.S. And because of this, this also leads to a significant amount of greenhouse gas emissions. And a lot of this has to do with the fact that we spend a significant amount of time indoors. For example, Americans spend about 90% of time indoors. And so we have to spend a lot of energy in order to make sure we are comfortable indoors, but as well as healthy indoors. And this became very important during the COVID-19 pandemic, when we found that a significant amount of the COVID-19 outbreaks occurred indoors due to poor indoor air quality. And so these are things that kind of need to be balanced, as we want to make sure we're providing safe and healthy indoor environments, but we want to also, try and minimize the impact on energy consumption and greenhouse gas emissions. And so what I'll talk about is a couple of different mitigation strategies that we can use via operation of the HVAC system. So first we will talk about the HVAC increased filtration to mitigate indoor virus. So here we have a kind of sample room where we have a sick person in the room that may be generating virus particles. And especially the lighter viral particles may remain in the air and begin to return through the air handling system. And some of these viral particles may be exhausted to the outdoor environment, but some may be circulated back into the supply air of the HVAC system and can return back into the room. But if we have some sort of an efficient HVAC filter set up, then this can hopefully filter some of those viral particles and limit the virus being recirculated back into the rooms. And so this is one common method to mitigate indoor virus through the HVAC operation. Another method is increasing the supply of outdoor air to properly ventilate the room and prevent recirculation of the indoor virus through the air handling system. So in this case, then we have our sick person generating viral particles, and they begin to return through the air handling system, but we disable the recirculation and the particles are exhausted to the outdoor environment, and then we just supply 100% outdoor air into the room to disable that recirculation of viral particles and to dilute the indoor air. And so in this work, then we focus on comparing efficient HVAC filtration as well as supply of 100% outdoor air. And in order to support these analyses and the different mitigation strategies, then we developed some new component models using Modelica language. In particular, we first developed a new HVAC filter model that has two key features. One is the removal of virus, as I kind of mentioned before, based on some defined efficiency, as well as we want to account for the pressure drop that the HVAC filter imposes on the airflow. As this is very important, in particular, some very efficient filters, while they're great at filtering particles with the airflow, they can actually impose a significant pressure drop in the system that can lead to consequences like increased fan energy or even reduced overall airflow rates to the building. And so this is very important to model with our Modelica models. I mentioned the removal of virus. For this, we simply just use assume a constant removal efficiency where the concentration of virus exiting the airstream is equal to the concentration entering the fill stream multiplied by some efficiency that defines the removal of virus. And in this figure, we show a simple demonstration of what this can look like, where we assume a room with initial 0 virus concentration being supplied with some supply airflow of concentration C9. And then we observe how the concentration would develop in the room with different filter efficiencies. And so we can see the most efficient filter, the red line, would then have the lowest steady state concentration of virus. Next, then we implement the pressure drop. This is kind of based on the existing pressure drop model in the buildings library. And so we model the pressure drop of the filter as a quadratic relation based on the mass flow rate, where that constant K filter is going to be calculated based on nominal values for the nominal pressure drop and then the nominal mass flow rate of the system. And so that here we show in the figure just a simple demonstration then of how the pressure drop would vary quadratically with the mass flow rates. And then we show this for different nominal pressure drop values. And then we can see we define the mass flow rate to be 1 kilogram per second. We see those curves all pass through their nominal pressure drop values at that point. And sort of setting that nominal pressure drop value is how we can differentiate between those different filters in terms of their pressure drops, where we might see more efficient filters have higher pressure drops. We then also implement some indoor virus transmission models in order to model the behavior of virus indoors. And so this first includes a virus generation model. And so for this, you can define some sort of a schedule of sick people in in the building that then generate virus particles at, in this case, we assume a constant rate. So that's our typical Modelica implementation where we multiply the schedule by a gain to represent the generation of virus particles in the zones. And so in this study, then we assume the sick people have kind of a typical 9 to 5 schedule during the week, Monday through Friday. And we analyze this throughout the year in order to understand the impacts of indoor air quality and the other strategies during different times of the year. Then lastly, we have our decay of virus model. And for this, we just use a simple first order method where the rate of virus decays in the room due to biological and chemical effects is modeled just based on a constant multiplied by the virus concentration in the room. And in this figure, we just show a simple demonstration of what this can look like. So in this case, we assume a room with initial concentration C naught, and then no other means to add or remove virus other than our decay. And we can see how the virus concentration decays over time, as well as with different decay constants. And we see that for the highest decay constant in the red line, then that virus concentration decays more quickly. It's just a simple demonstration of what this looks like. Now I'll talk about some of the methods that we use in this study. So after we develop these Modelica models and apply them to some sort of simulation study, then we need some metrics to quantify things like indoor air quality as well as the energy consumption. So first, we want to quantify the impacts of the virus concentration based on the predicted number of infections. And this is based on the Wells-Riley model, which is commonly used in these studies. And so for this, we first calculate the risk, which is a percentage, sort of a percent chance of being infected. And this is based on the amount of viral particles inhaled by an occupant. So that integral C of T dt is the accumulated virus concentration over time, and that IR is an inhalation rate, so to model or to represent how viral particles are inhaled over time. And so we can, then we want to calculate the predicted number of infections, which is multiplying this risk by the number of susceptible occupants. And so we can first look at the virus concentration to determine the risk shown in equation 1, and then multiply that risk by our dynamic occupancy schedule shown in that middle figure, where we can model some amount of dynamic occupants within the building or the zones. And then finally, we can calculate that predicted number of infections. And we do this by sort of integrating the risk based on the virus concentration and occupant schedule during times of constant occupancy in order to build this predicted number of infections metric. And this is sort of a probabilistic metric where, in this case, if you have a predicted number of infections around 1.5, then what we're saying is we're kind of predicting one infection with maybe a 50% chance of another infection occurring. And then, as well as determining indoor air quality for these different mitigation strategies, we want to calculate the energy consumption and then associate with that costs to run the HVAC system, as well as the associated CO2 emissions. And so for this, we calculate the costs based on filter costs to purchase and replace the filters, as well as maintenance, and then electricity costs based on powering the fan and providing cooling in the HVAC system, and then natural gas costs based on providing heating to the HVAC system. We then also, which these costs are kind of currently in practice, and then we apply a hypothetical carbon tax in order to determine or kind of equivalate the impact of CO2 emissions on these other costs. And so then in order to calculate CO2 emissions, we first determine the energy consumption during the day for both electricity energy consumption and natural gas energy consumption. So this is a day where some heating is required, and so we see the heating, natural gas energy change during the day, as well as the electricity to power the fan change during the day. We multiply the energy consumption by the emission factor that is associated with electricity as well as natural gas. For natural gas, we just have a constant emission factor that is independent of time and location. So we just assume that there's a constant emission to generate natural gas. Whereas for electricity, then this emission factor is dynamic based on things like the availability of renewable energy, as well as very much dependent on location, depending on what kind of electricity sources the different locations use. Then we can multiply those two together to get our final CO2 emissions. And so then lastly, we look at improvement in indoor air quality in terms of virus concentration, and then we calculate these costs and emissions, but we want to combine them and see in particular what is the improvement in indoor air quality relative to some increase in costs and emissions. So I will start by referring to, as an example, we will talk about MERV 13 filtration, which is more efficient filtration, currently recommended by ASHRAE to use during the pandemic, compared to a more moderate, less efficient MERV 10 filtration. And so for this, we first determine the percent increase in costs, where it's just the difference in the cost normalized by the cost for MERV 10. And for this, we use the sign convention in this way to make a increase in costs positive, as typically we compare the more efficient mitigation strategies relative to MERV 10. These will typically increase energy consumption either through increased fan power for the higher pressure drop filters or more cooling or heating energy for the increased outdoor air usage. And then we can quantify the percent improvement in indoor air quality per increase in costs by dividing the change in air quality by this calculated increase in costs. And in this case, then we determine a reduction or improvement in indoor air quality is, for example, a reduction in virus concentration is positive. And then that way we can be kind of consistent with our science. And this is typically what we'll see for the mitigation strategies, is they will improve the indoor air quality, but have some penalty in terms of costs. And so we apply our developed models for the HVAC filter and virus transmission strategies to the kind of standard prototypical 5-zone medium office building, which has an existing model in the buildings library based off the 2-week prototype, where we have this kind of typical VAB system with 5 zones, and in each zone we have those sick people generating virus based on their schedule, as well as we have implemented our HVAC filter model. And for our analysis, we studied 3 mitigation strategies. MERV 10, as I mentioned, which is a more moderate filter strategy, which has a virus removal efficiency of about 50% based on the assumed size of COVID particles, as well as a nominal pressure drop here of 143. And then we also look at more increased filtration using MERV 13 filtration, which has a higher removal efficiency, but a higher pressure drop as well. And then lastly, we look at 100% outdoor air as mentioned. And in this case, we assume that there are no virus viral particles in the outdoor air. So it essentially has a 100% removal efficiency. And it should be noted that this case still has a MERV 10 filter, and this is because you will still want to have some sort of HVAC filtration to filter outdoor contaminants such as PM2. And so, that's why we include the MERV 10 filter in this case, but really all that's going to be doing is adding that pressure drop to the system. And then we studied these strategies for 3 locations across the US with varying climate zones, as well as varying electricity sources. So for example, we have very cold climate of International Falls, which relies on fossil fuels like coal and natural gas for energy, or for electricity generation, but still uses some renewable energy as well. And then the hot humid climate of Tampa, which uses significant natural gas. And then a milder climate in San Diego, which is able to utilize some natural gas, but as well as more solar and wind energy, and have the lower emission factor. So for our results, first a broad overview of the results. we have a couple of trends here for the different climates and the different mitigation strategies. We first see the warmer climates tend to lead to higher costs than colder climates. This is simply because the warmer climates rely more on electricity for their for the HVAC energy consumption, because they require more cooling as opposed to heating, whereas the colder climate of International Falls relies more on natural gas heating for its energy consumption, and this gas consumption is much cheaper compared to electricity consumption, which is why we see much lower costs for the colder climates. But then on the y-axis, we see the CO2 emissions. And for this case, then we can see that the very hot and humid climate of Tampa leads to the highest CO2 emissions due to that significant energy consumption. And in particular, for the 100% outdoor air case in Tampa, this leads to very high costs and emissions due to the significant energy required to cool and dehumidify the outdoor air in this climate. So some trends for the indoor virus concentration. We'll look at a sample day in Tampa. And this is a summer day where the cases tend to use minimum outdoor airflow. And that is going to kind of differentiate the filter cases more from the 100% outdoor air case. And so for this, we can see how the virus concentration develops during the day, begins to increase around 9 a.m. when the sick people arrive, and then reach a more steady value in the afternoon, and then finally decay around 5 p.m. as the sick people leave and virus is decaying and removed from the HVAC system. And then we can also quantify the predicted number of infections of the day. And so for this, the predicted number of infections only increases during the day as humans inhale viral particles, and that risk increases over time, and then eventually reaches a constant value at the end of the day as the virus exits the rooms as well as the people leave. And so for this case, we see that the use of MERV 13 filtration can reduce the predicted number of infections by about 40% compared to MERV 10 filtration. And then actually the decrease from MERV 10 or from MERV 13 filtration to 100% outdoor air is actually somewhat small, I think about 5%. Then lastly, we want to quantify this improvement in indoor air quality per cost and emissions, as I mentioned before. And so we, calculate the improvement in indoor air quality normalized by the change in costs. And we see for two of the climates, International Falls and Tampa, that MERV 13 filtration offers the best improvement in indoor air quality relative to an increase in costs. And this is because MERV 13 can provide almost as good of indoor air quality compared to 100% outdoor air, kind of as I showed on the last slide, but with much less significant increases in energy consumption, especially in these climates with more extreme weather, either in the very cold climate where significant heating is required to heat the outdoor air, or in the hot and humid climate where significant cooling is needed. But we notice actually in the milder climate of San Diego that 100% outdoor air has the better improvement. And this is because in this climate, you can actually get away with using a lot of outdoor air without too much energy penalties. And so this is an example for the MERV 10 cases to show the dynamic usage of outdoor air in these two climates for kind of economization for these cases. And so we see in Tampa, you can use more outdoor air in the colder winter mornings, but for the majority of the day and in particular during the summer, you have to use more of the minimum outdoor airflow. Where in San Diego, due to the more mild climate, then significant outdoor air can be used throughout the entire year, with the exception of during kind of the peak of summer. We find that MERV 10 filtration is typically the cheapest and lowest emission option, but also has the worst indoor air quality. Use of 100% outdoor air can provide the best indoor air quality, but often leads to significant increases in costs and emissions, with the exception being in the milder climate of San Diego. And then MERV 13 filtration demonstrates the best improvement in indoor air quality per cost in two of the three climates, in particular in the climates with more extreme weather. And some future work based off this, we can apply these developed component models to study under building systems, as well as their performance under different control strategies. And here I have a couple listed journal publications based on this work that you can look at. With that, I'd like to thank you all for listening and for questions. Thank you. Yeah, that's a great question. So the question was, MERV 13, or the MERV efficiencies are based on different particle sizes and are different for different particle sizes. And so in this case, we assumed a constant particle size of 1 to 3 microns, and that's how we got those efficiency values. We did not consider any distribution of particles, but I think that is very interesting work that is that should be studied because the viral particles can vary in size and have some sort of distribution.
So how is the assumption of the infection model? Because you assume basically mixed air at full volume. So everything, all the virus would be completely mixed, which means that if I are infected, that over there these people at the same likely would be infected at immediate neighborhood. So how valid is that assumption?
Yeah, I think that's a great question. So I think in a lot of rooms, then actually the well-mixed assumption works pretty well, where just based on the ventilation system, then the air is close enough to being well-mixed that that assumption is valid. But there are also definitely rooms where that assumption is not necessarily valid, where you get stratification and more of a distribution of the concentration in the rooms. And so that's actually based on, or we have some related work that I'm doing with another lab mate of mine, where we actually use CFD to quantify that distribution of concentration within the room, especially in a room that has more distributed airflow patterns. Now, for these types of annual simulations, it's kind of difficult to apply like a CFD simulation since it's incredibly computationally intensive. So that's why we use this kind of well-mixed model for this case.
So I also been thinking about the standardization of the model check. If I tell my head over there and talk to my neighbor, it's basically check for viral loads that he's directly exposed to. And I thought, that's the motivation of the distancing goal, right? The total distancing, which is something that's not affected not the result in the model assumption.
Yes, that's definitely correct. And so that's why I think, yeah, using those kind of CFD models can be beneficial. But I would also say, for those jet effects, they are sort of short-term effects, and hopefully that's just like a short-term dynamic versus a more steady state distribution in the room.
Thanks everyone for attending the session, and I apologize for the session going a little over time. Yeah, I guess we can.
Oh, yeah. Oh, yeah, sure. Yeah. Yeah, you can. And it's detect, yeah. Oh, yeah, shift. It's getting the balance. Maybe, yeah, probably the other one. Yeah. I better. Have you stopped recording? Oh, no. Okay, but let me double check if it's.
I just
Okay,
turned the camera on.
Okay,